I'm Ryan. I'm a science teacher.
I'm Cheryl, and I slept through science.
Each episode will tackle a science question you may have learned in school, but can't quite remember or fully explain.
And I'll take the risk of asking the dumb questions so that we can all understand the science we slept through.
The bell has rung. Let's get started. Welcome to Lesson 7.
Oh, man, Ryan. So this podcast has just been bringing up like moments in science class that are coming back to me. And so it's usually like in a weird nightmare that I'm having, and then I sit up and wonder if I'm failing. But
Oh, no.
no, not really.
Oh, jeez.
But I'm remembering this science class I was in. I'm going to say maybe it was like a physical science class in college. Does that sound like a thing that they would have people who are
Maybe?
not studying science?
Oh,
take?
yeah. Yes. In college, typically most liberal arts colleges will require non-majors to take one lab science class. And
Okay.
they typically have classes that are designed for the non-majors versus the classes that are for the majors.
So maybe that's why this story came up in this class, or maybe the science teacher is funny in all of his classes. I hope so, because this is a funny memory to me that like
Okay.
makes me chuckle when I think about it. He was talking about car crashes. So he was talking
Car
about
crashes make you chuckle?
yes, they're hilarious.
Okay.
He was talking about like if you're driving a small car, you're going to get more impact on you. Like it's going to be a worse situation for you as a driver if you're in a small car than if you're in a bigger car. And he
Okay.
was explaining why. And do I remember why? I mean, we're going to find out today if I remember why. But then he was saying, so really, like you're in a semi truck, it's going to be a really good situation for you. And, you know, depending on the type of car you hit compared to the size of your car, it could be worse or better. And he was like, but really, if you're going to get in a car accident, just make sure that you're hitting a pedestrian.
Did he say why?
Because then it'd be the least damage done to you and to your car
Okay.
if you're hit a pedestrian. And then he was like, and really don't hit like a telephone pole or something like that. Kind of for the opposite, the flip side of that, of like there's going to
Okay.
be a lot
So
of damage done to you in your car.
aim for the pedestrian, not the telephone pole.
So if you have a choice,
Oh
you're
my
spinning out
gosh.
of control and you can either hit a person or a pole. Definitely, I mean, hit that person because you don't want to ding up your hood, you know? So
Right. Yes, that's definitely where the priority should be. The damage on your vehicle, not the damage to another human being. Sounds right.
I mean, even though I can't remember the details of this concept, this story helped me remember this
Oh, sure.
concept. Like, I don't
Yeah.
remember much from that class, but I do remember that story. And it made me laugh that my science teacher, who was also like a nice Christian man, like told me to hit a pedestrian. So, yep.
Perfect.
Yeah, it was great.
So it sounds like the big question behind this story is why would you do less damage to your car if you hit a pedestrian than if you hit a telephone pole?
Yeah.
Is
Yeah.
that accurate?
hmm
Okay. Well, we're going to start with the pre-assessment.
Okay.
Why do you think you would do less damage to your car if you hit a pedestrian than a telephone pole?
Okay. So I'm thinking it has to do with okay, well, it has to do something with like the objects and motions things.
Objects in motions things. Okay.
Yep. But I'm gonna say it's because if you are hitting something that is bigger than you, I'm gonna compare a person to like a truck for a minute.
Yeah.
So, and if I'm in my little Volkswagen Bug, if I'm gonna hit something that's bigger than me, then I feel like the size of it has an impact
No pun intended.
on, but also maybe it has an impact on my smaller vehicle. So I'm going to say that a larger object, I'm going to say its size has something to do with it.
Okay.
That if it's bigger and heavier and my smaller and lighter thing hitting it, it's gonna hurt me more than I'm gonna hurt it, or I might like go flying while it would just kind of like because of the size. I'm gonna say the size. Like even if we were driving at the same speed, because I know speed has a lot to do with it too. Like if you get in a car accident at 60 miles an hour, it's very different than 5 miles an hour. But so I'm thinking speed is a piece of it. But even if we were going the same speed, I think that the bigger object is going to do more of the damage because there's more like oomph behind it than my little car. So then if I had a person, it I mean, okay, if we go even more extreme, if a bug hits my windshield, something has hit my car, but it's so tiny, it doesn't make any difference on my car. It doesn't even damage my car. It doesn't slow me down. So then a person feels like, I mean, it might leave a dent, but I could probably still be driving.
Okay. Sure.
Just because they're still not big enough to stop me or
Mm.
damage me as much. And then if I had a pole on the other side of this, um, there's probably the factor of that the pole is also like in the ground. Because if there was a pole sitting on the ground, it would probably leave a dent, but also go flying. But if it's like in the ground, then I can't think of like a fancy term for it, but like I'm just gonna stop. And because it is not, I don't know if it has to do with it moving, but it is fully stopping my car, which means it feels like that would do even more damage. And also it it's so big. Is it just size? Yeah, it might, but it might have to do with that the pole wasn't moving. I don't know if that makes a difference or if it's just because the pole is so firm and standing in place. But yeah, me hitting that would fully stop my car, which would then, it feels like, hurt me even more that I didn't just bounce off of something and keep going. Like there's a bigger change in me, like going whatever to 0 miles an hour. And all of that impact is going to be on me and my vehicle. So, yeah, those are my thoughts as far as why you should always hit a person when you get in a car accident. I hope that's what the kids take away from today's lesson.
I'm sure that's what
Yeah.
they'll remember. 'Cause that's what you remembered.
I know. Yeah.
All right. So based on your pre-assessment, you've got some pretty good ideas already that I'm going to build
Ooh.
on. And then I think I should be able, if I'm good at what I do, to connect it to some science concepts so that hopefully it does make some sense and maybe you can get some sciencey terms to go along with some of the ideas that you have as well.
Cool.
The first thing I'm going to do is actually basically dismiss part of it. So you talked about speed a little bit and how the higher speed means there'd be more damage. And that's correct, right? Like if you said if you're going 60 miles an hour
Yeah.
versus 30 miles an hour.
Yeah.
But that is a whole different aspect of this whole
Cool.
thing. And so I'm just going to kind of set that one aside for right now. And then maybe that'll come up as a question in a future lesson. But for now,
Great.
we're just going to focus on really what you said you thought the biggest thing was size.
Yes.
Right? Like that was the
Yes.
biggest impact. So we're just going to focus in on size and see if we can use that to explain. One of the things that you said is that bigger objects are heavier and then they also have more oomph, is what you
Yes.
said.
Yes. That is my very sciencey term, is they have more oomph.
Well, believe it or not, that's actually a really helpful word to kind of understand part of what's going on. First thing, because I'm a science person, I do have to say that, and I think you probably would recognize this too, just because something is bigger doesn't always mean it's heavier,
Yeah,
but it
it's like
does
a pillow.
usually. Exactly. But it usually means that something's heavier. So we can use that as an approximation, right? If you have one object and you have more of that same object, then it's going to be heavier.
Yes. Or like a
Right.
car in
Right.
general. The larger
Exactly.
car will be
A
heavier.
larger car is going to be heavier. Right.
Okay.
So perfect. And then therefore I'll have more oomph. Now, when you say oomph, what do you kind of mean by that?
Like it's going to be a bigger impact.
Okay. Like if it hits you, you mean?
Yeah. Like it's going to cause more damage,
Mm-hmm.
and it's going to um gosh, I'm trying to think of how else I would describe it. Like, if I don't know, if a stronger person hit me, it would hurt more. Like, so it's gonna hurt whatever that thing is more. But
Mm.
I'm trying to figure out what I'm actually meaning by hurting it more. But and
Yeah.
that's why I can only think of saying causing more damage, but like
Yeah.
having a bigger like physical impact, essentially.
Sure. So let's think about it this way. If we're not talking about a collision for a minute, because it seems like that's where you're maybe because that's the context we're talking about. So maybe
Yes.
if we move out of that context. So if instead we talked about like, I don't know, an elephant or a dog, which one has more oomph
The elephant,
and why?
because it's heavier
Okay.
and because it's bigger, but mainly
Yeah.
because it's heavier.
It's bigger and heavier, right?
Yes.
And you could know that because one way to kind of think about an informal way of measuring oomph, if you will, would be if something's sitting there and you wanted to push it, right?
Yeah.
How much, which one would you have to push harder on to get it to move
The
more,
elephant. Yeah.
right? So it has more oomph that you need to overcome to get it to start moving.
Yes, which means it's also then harder to get it to stop moving.
Exactly. It's kind of two sides of the same coin. Right? So if you
Mm-hmm.
have something with a lot of oomph and it's moving on its own, it also is going to keep moving and it's not going to want to stop as easily.
Yes. Yeah.
Right? And then same thing, bring it back to the car, right? A little car versus a semi. The bigger
Yes.
car has more of that oomph, which is why it can cause more damage, like you're talking about.
Because it
But really,
takes more to stop it. And so the object that is stopping it will get more damage or feel that impact more because it
yeah,
is taking more to stop that thing.
yes, yes. So that concept of oomph is actually a scientific concept, believe it or not.
Ah,
It's
yeah.
called, and you actually probably heard the word before, it's called inertia,
Oh, yes. Yes. I've heard
right?
this word.
And anyone who has ever watched an episode of Bill Nye the Science Guy has actually heard this word before. Because in the
Really?
beginning, yes, one of the little things in the opening is inertia is a property of matter. It's
Oh,
one of the things
cute.
that they say in the opening. So most
The
people probably don't
property
remember
of
that, but I do. I've also seen a lot of Bill Nye episodes more recently than a lot of
Of
people
course
do.
you are. I mean, you're a science teacher, but you might have even seen Bill Nye recently if you weren't. So,
That's true too.
Mhm.
Yeah. So it's called inertia, and it's actually one of Newton's laws of motion.
Oh,
Da-da-da-da. So
oh,
it's
yes,
his,
I've heard of these.
yeah, Newton has 3 laws of motion, and inertia is the first one.
Okay.
Oftentimes it can be said objects in motion stay in motion, and objects at rest stay at rest unless acted on by an outside force.
And that's the law of inertia.
Yep. Which is
So,
just
is
the
that the
oomph.
definition of inertia? Or that's the
No,
law of inertia?
that's the law of inertia.
What's the
Newton's.
definition of
So
inertia?
the inertia is, it's okay. Now you're really going to push me. The actual definition of inertia is it's related to the amount of matter in an object, the amount that that object resists a change in motion. So the more an object resists changing motion, either going from rest to moving or from moving to rest or changing a direction,
Mm,
right? While it's moving, any of those things, or speeding up or slowing down, even if it's already moving and you want it to go faster, or it's, already moving and you want it to go slower, but not stop it. Any change in motion, it resists it. It's harder to change the motion
got
of
it.
something with more inertia.
Okay.
And that's connected to the amount of mass or matter something has, which the easy way to think about that is just think about it as the number of atoms in something. Technically, it's more complicated than that, but
Okay.
it's close enough.
Okay.
Right? So if something has more stuff in it, more atoms, right? So that's where that bigger, like you talked about, bigger, heavier, that's generally connected to having more atoms in it. That's going to have more inertia. It's going to have more oomph.
Got it.
Good so far?
Yes.
Okay, so let's add the next piece then. And I kind of already mentioned it, which is in order to change something's motion, you need to have a force, which is just a push or a pull,
Okay.
right? Like
A
if
push or a
you
pull.
wanted to get an elephant moving, you would have to push the elephant or pull the elephant,
Yes.
right? Same thing for a
So
car. Go
hold
ahead.
on then.
Yep.
When Obi-Wan tells Luke to use the Force,
Uh-huh.
he's really just saying use a push or a pull.
Well, that force is a little different. That force is an energy field that surrounds all living things.
Okay. And that's what your shirt is about here?
So my shirt is "May the Force be with you," but this is the equation. This is actually a calculus equation for how to figure out what force is in physics.
You're a nerd.
Yes, I am. And so we're kind of we talked about the M already. That's sort of where inertia is represented because that's the mass, right? So something that has more mass has more inertia.
Okay.
And right now we're talking about the F, the amount of force. And
Got
then we'll
it.
talk about this weird dv dt thing at the end.
Okay. And force is a push or a pull.
Mm-hmm.
And
Force
the
is a push or a
law of
pull.
inertia is that objects at rest want to
Yeah.
stay at rest, and objects in motion want to stay in motion.
Yep. Unless acted on by an outside force. So that's how you change something's.
Oh, unless
They call it
pushed
state.
or pulled.
Exactly.
Okay.
Right. So you can get something moving by adding a force to it.
Okay.
And you can stop something from moving by adding a force to it.
Got it. Like
So
when I hit a bug.
Like when you hit a bug. Yes.
Yes.
So we've got the mass, the thing with oomph, right? It has inertia, and you can change its motion by adding a force, a push or a pull. And when you do that, and you kind of talked about this already, you said that like you can have a bigger change in a thing.
Yes.
Right? And what it is that we're changing is this kind of third component, and that's the acceleration of an object.
Okay.
Now, when you hear acceleration, what does that make you think?
Speeding up.
Right.
Like putting my gas pedal.
Yes. Yeah. Sometimes we call it the accelerator, right?
Yes. Yeah.
Yep. In physics, acceleration is a little bit broader than that. In physics, acceleration is any time the motion of an object is changing.
Oh.
So speeding up is an example, but technically so is slowing down.
Oh, isn't that what other people call deceleration?
Yes.
Okay.
Yep.
But deceleration and acceleration in physics are both acceleration.
Yes.
Okay.
We consider them both an acceleration. And we also, to even make it more complicated, if you're going at the exact same speed, but you're turning, we call that an acceleration also.
Is this like when I try to talk to kids about consequences, and then I'm referring to positive consequences, but they think consequences are
always negative? Mm-hmm. It's kind of like that. Yeah, actually. Yes.
Okay.
And it doesn't mean that the word deceleration is wrong. It's not. That's what we use in common everyday language.
And
but
it helps
physics,
in our language too.
It does. But in physics, any of those things count as an acceleration.
Okay.
And that's actually where the last part of my shirt comes in.
Okay.
Now, again, this is the calculus version. So dv over dt, that is a derivative. V is velocity, t is time. And velocity over time is how we calculate acceleration. So velocity is kind of like speed, and in the amount of time it takes you to do that.
So that's why a car crash would be like the time is almost instantaneous.
Yes.
And so it's a very short amount of time.
And your velocity is changing a lot in a very short amount of time.
So it's going to be really dramatic.
So it's a big acceleration. Yes. So that leads to sort of the last piece here. And I'm actually going to share my screen with you.
Okay.
If I can be smart.
And I'm just going to put a plug out for our video podcast. If anyone is listening to this and wants to watch Ryan's cool shirt and his screen share, which so far is almost a blank screen, but we'll see how this goes. They can check out us on the YouTubes.
On the YouTubes.
Yes.
That's right. That's right. So, and I'll do my best to kind of verbally describe what I'm writing down also, but I think it helps to kind of have the visual to go along with it. So we talked about force. if I can get this to right, which we use a capital F to represent,
Okay.
and then equals M for mass. And then on my shirt, like I said, it's the calculus version. There's a simpler version that just uses algebra. And like I said, it really just means acceleration, which we just use a lowercase a to be acceleration. So F equals M times A, or MA.
Oh, I like this one better than the calculus one.
It's a little bit friendlier than the calculus one. And this is actually Newton's second law.
Oh, good job, Newton. Just pulling it all together like
Right?
that. He was onto
Exactly.
something there.
He was definitely onto something. Okay. And so it shows all three of them. But what it also does is it gets at what you're saying. So as you change these values, they affect each other because it's all in an equation.
Oh.
Okay.
Okay.
And so,
So can
go
I
ahead.
give you an example then?
Yes, please.
Okay. So our M
Mhm.
is our person.
Yep.
And so the force is A is my car hitting the M, the person. And it's going to be a lot of force. It's going to really hurt that person, which is the F. Did I get it? Did I do it?
Sort of.
Okay.
Sort of. So your car, so you actually what we're actually doing is comparing two of these. One for the car, one
Oh.
for the person.
So we would do two equations?
Sort of. So let me take a step back first, though.
Okay.
Okay. So we just need to figure out how they change in relation to each other. Okay.
Mm.
So we talked about the acceleration getting bigger, right? Like if you stop all of a sudden, that's a very big acceleration.
Yes.
Right. But the mass wouldn't really be changing very much.
Yeah. Yeah.
Okay. So I'll make up some numbers. These are not real numbers, but let's say that the mass was, oops, that's the wrong button. Still wrong button. There we go. So let's say that the mass was like 10 kilograms, because that's a nice, easy number. Okay. And then I'm going to say that the acceleration is really small, 1 meter per second squared, because that's as simple, right? Like you could multiply that in your head.
Sure
right?
could.
10 times 1 is
10.
10. So the force is 10, and the units we use for force are newtons. Guess where that name comes from?
You know what? Here's the thing: is I'm glad he got the trademark on this whole third, first, and second law and this whole force thing. So I feel like he earned it. So
Yep,
I'm gonna give that to him.
Okay.
Yeah.
Right. So like this would be one circumstance, and this would be, let's just say that's a normal acceleration when you're braking. Again, I picked numbers that aren't real just to make the math easier. Okay. But now if we do that same thing again, but we're going to increase the acceleration.
Okay.
All right. So I'm going to do the same thing. I'm going to write it over to the side here. So our mass is still the same, 10 kilograms, right? Because like your car hasn't changed.
We're saying like my car is the 10 kilograms.
Yes.
So these are both just in reference to my car.
Correct. Just in reference to your car. But
Great.
now we're going to say that acceleration is a lot bigger. Because like you said, it's changing that velocity over a really short time.
Yes.
Right.
Yeah.
So let's say instead of 1 meter per second squared, it's 10 meters per second squared.
Okay.
Now what's the force?
100.
It's 100. Yep. 100 N newtons. Right. So even though the actual vehicle is the same, right? When you increase the acceleration, you increased the force.
Okay. Yep.
Right. And so that means there's a bigger push or a bigger pull.
Okay.
Right. So like that push, like that's the thing that's going to cause damage.
So that person would rather get hit by my Beetle than by the semi truck.
Yes. Because why?
Because even if the acceleration was the same, like if the truck and I were driving the same speed, the mass of the semi truck would be much larger, which means the force would be much greater.
Exactly.
More newtons. And everyone knows we hate a lot of newtons when it comes to car crashes.
Well, I mean, if you're on the receiving end, yes.
Yeah.
So one way to kind of look at this kind of conceptually is, and this is where we're going to see if I can make this work. Let me actually make the force about the same size and not quite so big. So it's like this, right? F equals ma. Well, if I were to take that acceleration and I were to make the acceleration bigger, right? That is also going to make the force bigger.
This has made all the screen sharing worth it. Seeing you drag letters to make them large.
To make them bigger, right? Like, does that make sense?
Yes. Yeah.
Right?
Totally.
And then the flip side is the other thing that you said, right? So also, if I were to make the mass bigger, oh, now my A's.
That's okay. I understand.
Right? Then the force would also have to be bigger.
Yes.
In order to keep them the same.
Yeah.
Does that
makes
make
sense? Yes.
Okay. So even without numbers, you kind of, it's like that's the way those relationships work. Right?
Yeah.
So as one goes up, the other one also goes up.
Yeah.
And so now if we take it back, and you kind of have already done this a little bit, right? Now if we go back to the cars, right? And I actually like the idea of the bug hitting the windshield.
Oh, yes.
Right?
Yeah.
Because I feel like that's a really good example. So if we do this, now we've got two different, whoops. Helps if I do this the correct way. Oh boy. Now what? There we go. Let's try this. So if I move this guy over here, and then I'm going to copy it and paste it. Oh, I don't know if that pasted. There we go. Okay, so I've got another one over here, right? And so one of these can be the car, and one of these can be the bug.
Great.
Right? And so in this case, their masses are different.
Yes.
Right?
Yes.
Okay.
Now but here's a question, though. This might be getting too in the weeds, so you can stop me if you want. But if the bug is hovering and not moving in any direction, and my car is going down the freeway, is our acceleration the same when I hit it? I didn't think so.
So there's a couple of different things. It all depends on what you're defining. So in that moment, the two accelerations are not the same, right? Because the car is accelerating more than the bug.
Okay.
Right?
Mm-hmm.
But when they come into contact, that causes a new acceleration.
Oh.
Because now when they come into contact, they're pushing against each other. So you've added a new force.
Interesting. So that's like its own separate little world.
Well, and that's actually what we're doing right here.
Oh, okay.
Okay. So like the car, let's say it has 1,000 kilograms. And let's say the bug has, this could be 0.1 kilograms. Because it's not a lot.
Minuscule.
Okay? And that's even probably more than it actually
generous,
has. It's probably, smaller than that. Okay. When they come in contact with each other, they actually are going to experience the same force.
Wow.
And that's actually Newton's third law. We're going to do all three.
Man, we are covering a lot today.
Right? And this one, I guarantee you've heard before too. Every action has an equal and opposite reaction.
Oh, yeah, because that's a line in Hamilton. So
there you go.
Yeah.
That's where Newton got it from.
Oh, he got it from David Diggs? I did not know that. Wow.
That's where it came from.
He was like, ooh, I wonder if I can prove that in science.
Yeah. And it took him a long time to figure it out. But so what that means is when the car hits the bug, technically the bug is also hitting the car.
Yes.
Right?
It just doesn't necessarily seem like it.
It doesn't seem like it, but they are both hitting each other, and the force between them is the same. Now I'm going to totally make up what the number is for the force. Let's just say that we go back to our 10 kilogram. Okay, what's your O?
Well, I'm Oing because I was wondering, like, is the acceleration secretly the same because of this impact? But actually the force is the same.
Mm-hmm. And this is where the issue comes in.
Interesting.
So now, and this is a little bit trickier because you'd have to technically do a little bit of algebra. 10 divided by 1,000 is 0.01. So this one is Did I say 0.01? Is that what I said?
I think so.
Yeah, I did.
Yep.
0.01. Whereas
Okay.
this one over here, this is where you have the
The
100.
bug. The bug side is 100 and the
Yep.
car side is 0.01.
Yep.
Which
So the
would make
car,
sense because the bug isn't experiencing a dramatic difference in his day.
right.
And the car doesn't even care.
Correct. And when it's accelerating that fast, all of a sudden, that's why it ends up getting squished.
That bug is dead.
Because like technically like the front side of it experienced that acceleration before the backside does. So it accelerates into the backside.
Oh, wow.
Yeah, it's not good.
All right. And the car will not even have a ding on it because the acceleration is 0.01.
But technically it does experience a slight acceleration in the opposite direction. It's just so small. Again, these numbers are made up, but
yeah.
So going back to the original question then.
Yes.
Why would you want to hit a pedestrian instead of hitting a semi-truck or a telephone pole or whatever?
Because my car would experience less acceleration if I hit a person.
And why would your car experience less acceleration?
Because the mass. Yeah, because of the mass. The mass of whatever I'm hitting is smaller. So like the mass of the person is smaller than of the semi-truck. Or let's not even get quite into the telephone pole because I feel like there's some other elements at stake.
They're all
with it being planted into place.
Yes, and you mentioned that, right? And all really, and there's a lot of other things we could get into, statics and things like that. But basically, you can think of when the telephone pole is planted in the ground, it's able to provide a larger force.
Oh, okay. Yeah.
Like that's basically because it's not going to move as much. It's going to resist it more. So it can provide a larger force.
Mm-hmm. Okay.
That's the basic way to look at it.
So when my car experiences more acceleration, more damage is done to it.
Yes.
Cool.
Or conversely, if it's the same amount of acceleration, if it's feeling more force for some reason, right? Like there's going to be more force involved in a collision with a telephone pole than with a person because the telephone pole has more mass.
Yeah.
So you can mean that both ways.
Yay.
Okay, Cheryl, it's time for your favorite part of the lesson.
The part where you let me leave and go to recess?
The pop quiz.
Is it really a pop quiz if we have this every time though?
I don't know. I don't give pop quizzes in my classes, but apparently some teachers
still do.
Well, yes, but I've also heard from some students that like a teacher gives a pop quiz every Wednesday. I'm like, how is it a pop quiz if you know it's every Wednesday?
That's just the definition problem then, but
So I don't know. All right. Are you ready?
Yes.
Okay. First question. What word do scientists use to describe oomph?
Inertia.
Okay. And what does that word mean?
What does it mean, or what's the law of it?
You could use the law of it.
I will tell you the law of it because that feels easier to me than the definition. The law of it is that objects at rest want to stay at rest. Objects in motion want to stay at motion unless they are acted upon by a force.
Beautiful. I love that answer. Speaking of, question 2, what is a force?
A force is, well, now you have to like cover your shirt to, make sure I don't cheat. Unless this is like an open book quiz, one of those.
I can't stop you.
Yeah.
You're on the other side of Zoom.
Okay, so force is mass times acceleration.
That's how you can calculate force.
Oh, that's right. But force is a push or a pull.
There you go. Yep. And so this one is, you'll get this next one, no problem. So what are the 3 things we need to know about an object in order to use Newton's second law?
It's force, it's mass, and it's acceleration.
There you go. You got it. Yeah. You're 3 for 3. Okay. So these last 2 questions are application questions.
Okay.
You ready?
Yes.
if the mass of an object stays the same,
Okay.
but more force is applied to it, what happens to its acceleration?
It goes up.
Bingo. Last
That's what
question.
an application question is?
Yeah.
Oh, okay. Maybe
I
I'm
mean-
thinking
I
of
mean,
like story problem.
A story problem is a type of application question.
Oh, okay.
Yeah.
You're the educator. Well,
All right, last question. When two objects with different masses collide, what happens to their accelerations and why?
both of their accelerations change.
Okay.
The acceleration of the smaller or the mass, the object with a smaller mass
Mm-hmm.
would be a higher number,
Mhm.
and the acceleration of the object with a larger mass would be a lower number because we are dividing, because the force is the same. And so we're doing division, but we're dividing by different numbers. And when we're dividing with the larger number, we're getting a smaller acceleration.
Perfect answer.
Yeah!
100%. A plus.
Yay! My first A. No, sometimes I
first
got an
A.
A in school. Not in science, though.
Well, you're getting an A so far in our science class.
Oh my gosh. I'm going to call my college professor and tell him that I don't remember his name. So I don't think I can call him.
Well, I didn't really use any special resources or anything in this episode other than drawing a little bit, but there are a few cool things on the internet if people wanted to check out some more stuff. So
Cool.
let me recommend a couple of things. The first one is, Cheryl, I really think you need to go back and watch this. So it's a YouTube video, and it's an old school, like probably from the 70s cartoon about science that you would like maybe show in your class. And it's a series called Eureka. And it's episode 1, Eureka, which is about inertia. And it's hilarious. It's little cartoon characters,
Cute.
and they're just kind of introducing the concept of what inertia is. So
That sounds great.
It is. It's great. It's very cute. You'll like it. So that's the first one. The second one is also a YouTube video, and it's going to approach things from a slightly different perspective than what we talked about, but it's from a YouTube channel called Minute Physics. So
Okay.
they do they're not always a minute long, but short little videos about physics topics. And this one is the physics of car crashes. So it's good. It goes into some of the energy stuff that we didn't talk about this time. And also they talk a little bit differently about acceleration and why that matters, but also how they design cars to try and account for that.
Ooh,
to help
that's
us when we do get in
cool.
crashes. So it's a really cool video. And so we'll put the links to both of those in the description for this episode.
And my one that I'm going to share is that, Ryan, which of the Star Wars movies does Obi-Wan tell Luke to use the Force? Is it like 4, 5, and 6? Or is there a specific, what's that quote? I can hear it. I can hear him saying, is it when he's a ghost man?
Yes. Use the
so which
Force,
one?
Luke.
Yes.
Let go, Luke. It's when he's flying through the trench on the Death Star, the first Death Star. So that's going to be
Yes.
episode 4.
Okay, well, that's what I'm going to say. I think our listeners and our viewers should watch episode 4 of Star Wars to learn more about Star Wars Force.
I completely agree. And then, of course, if you wanted additional information about the Star Wars Force, you'd also have to watch Empire Strikes Back, because that's where he meets with Yoda, and Yoda describes the Force a little bit more too. So you probably have to watch both.
Okay. Yeah. That's good.
Yeah. All right. Well, we got about 5 minutes left, so it's time to go ahead and pack your stuff up and get ready for my closing remarks. You can follow us on Instagram and Facebook at I Slept Through Science, or on Twitter at Slept Science.
If you have dumb science questions like I do, please send them to us. You can email us at isleptthroughscience@gmail.com, or you can even send us a voice memo and we'll play it on the podcast.
Please rate and review our podcast to tell other people what you think about it, subscribe to make sure you don't miss an episode, and share about our podcast on social media.
Thank you to Beth Reed Miller for the artwork. You can check out more of Beth's artwork at Beth Is Something. Okay, great. Thanks. Bye.
Ah! The bell doesn't dismiss you. I dismiss you.